So let's get started on the quantum computing and quantum information. And okay, I want to make clear what to expect. Okay, here, you won't be an expert in quantum computer after Thanksgiving. Okay, just think about if you go into a coding class in computer in computer science department. Okay, after a few weeks, you won't be expert on coding, right? So if you want to be a quantum expert, well, spend the next 2 or 3 years working on it. Okay. So the realistic goal, okay, of this, I think from now to Thanksgiving there are about 5 weeks, is to understand, okay, why do we quantum computing and quantum information. Okay, the first question is, why do we need quantum computing? Why do we need quantum information? Right? Why people are actually looking into this, right? And we actually spend probably half an hour explaining why, and then it will be very convincing. Okay, and the second one is that, okay, people have been talking about quantum computing and quantum information since 1980s, since Richard Feynman and then other scientists suggested it. So it's been almost 40 years, and then you still don't have a quantum computer. And the Google's claim quantum supremacy, which is true for that specific task, that's similar to generating a random number. Okay, so it's not really a useful quantum computer. And that was actually one of the final project from last year, is that having the student explain, okay, that paper, Google paper. So why it's difficult? Okay, why it's difficult? Okay. And then third, I want to show you guys some examples that the quantum computing and quantum information, okay, in some special case which is already known to us, is fundamentally better than classical computer or classical information processing. Fundamentally better means that quantum computing and quantum information can do things that classical computer can never do. Okay, that's the definition of fundamentally better, can never do. Okay, so this is kind of the interesting thing that I don't know if you guys if you guys know that the Congress actually want to invest billions of dollars into quantum computing and quantum information research. I think the bill was passed in 2018 or 2017, and then the actual reason is that the U.S. Congress and also the military was surprised by the quantum satellite launched by China. Okay, and then so a lot of development nowadays, actually right now it's still friendly competition because we're all so far away from it. Even the quantum satellite is very nice paper, but not really useful. I hope I can still go back to China. Okay, so the reason that people are actually working on this so hard, like the different countries investing many monies onto it, is that because this is fundamentally better than classical computer. Once you can do something that people cannot do, you get a strategic advantage. Okay, and that advantage is like exponential scale, right? For example, the U.S. is the first country to have a nuclear weapon, and it scares most people out, right? So, but then how do you keep people not using nuclear weapon? Is to have multiple countries having nuclear weapon. Okay, so this is the same thing. Okay, so any country that have a significant lead in quantum computing and quantum information is not a good sign for the entire world, right? So you should have U.S., should have Europe, Russia, China, and then probably some other nations all invest into this, and then probably keeping relatively similar level, so that to make sure that this new technology, when it was ready, when it would be ready in the future, would be primarily reused for civil use and not meaningless military use. Okay, now let's first, well, we have 25 minutes, and then I think we can answer why quantum. Why do we need quantum computing? Okay, so the idea is that there will be some task that your classical computer can never do. Okay, I know if you guys go to computer science class, people will actually tell you, okay, there's hard problem, NP hard problem. Those are one type. Okay, there's some type of problem that's to our knowledge, there's no existing algorithm to solve it, okay, efficiently. Okay, those are one type of problem that classical computer right now cannot do. But that's not the point we're trying to make here, because those problems, if someone is really genius and figure out algorithm, actually can make the NP-hard problem to a much easier problem. Right. So the difficult level or the complexity level of solving something actually depends on your algorithm in a classical computer. Right. So that doesn't mean classical computer can never do that. It just means people are not smart enough to figure out that. But then there's something that classical computer probably cannot do. Okay, is to calculate quantum mechanics. Okay, and then the way you can think about it is very interesting. It's based on the fact of something called, well, we learned it in the first class already. It's called superposition. Superposition, meaning that your particle, right, your electron can be simultaneously be in many different states, right? And then just like the Schrodinger cats, right, you guys answered in the midterm. Right, now let's ask this question that is being asked by a lot of chemists and then biologists. Right, the question is, if I give you certain atoms and then you put them together, what type of molecule can I get? Right, what type of molecule can I get? This is a very, very simple question. Unfortunately, there's no answer. Okay, unfortunately, there's no answer. I think people kind of stop at protein level using classical computer at protein level around 60 to 100 atoms. But again, I'm not up to date. Maybe there are many new development these years. And the reason that classical computer cannot calculate furthermore is because of the superposition. Right? Now let's think about this example. We simplify what chemists and biologists they do. Let's just think about, okay, if we have n atoms. And then these atoms, well, the real atom actually has structures, and then they have many different states of your electron. It's more complicated, but that's for the simplicity here. Let's say the atom can only be in ground state and excited state. Right? There's only two states your atom can be in. Now, the question is, for n atoms, how many total states can you be in? Right? Each atom can be in two different states. How many total states are there? Right? And this is probably, you guys are familiar with this. If you do statistics, you know that if n equals 1, then there are only two possible states, right? One is ground state, the other is excited state, and then you're in superposition. And then if n equals 2, then now things become a little bit interesting, is that you can have both of them in ground state. Okay, the first one in ground state, second one in excited state, and then first one in excited state, second one in ground state, and then also both of them in excited state. Right. So in total, you have 4 possibilities, and then you need 4 parameters to describe the superposition. And then you can quickly see that the number of possible configurations, okay, of your states is 2 to the n, right? 2 to the n. And then to completely describe this state, the superposition state, you need 2 to the n alpha, right? Each of these possible configuration has a coefficient in the front that describe the weight of it and also the phase of it, right? So you need 2 to the nth state, 2 to the nth parameters, okay, to describe this thing. And the exponential law is actually very brutal, right? So suppose n is 100, and then you can actually calculate, okay, so you need 2 to 100 parameters just to describe the state, not to calculate, just to describe. And this is around, okay, you can do this, but first do a 10, and then there's another 10 here, so in total you get 10 to the 30. Okay, you need to 10 to the 30 parameters to describe this superposition, just describe it. So it's 1 followed by 30, 0, okay? And if you don't, we normally don't have idea of how, how big the number is, right? So let me give you an example, okay? The first is that our existing, where's the number I put it? Okay, the existing data center nowadays store roughly 10 to the 21 byte in the entire world, right? That's the amount of data we store, okay, in data center. And if you count personal computer, maybe there's a little bit more, but then that's how much data we store, right? So if you use all the data center in the world, you can't even store the coefficient of the superposition, not to say calculated, right? Just not possible to store it, okay? But then you might wonder, okay, that's not a physical hard limit, right? So there could be a technology leap in how people make the storage, okay? And now I'm going to make the argument that that's a dead end, right? It's not going to work. Is that suppose, okay, suppose we're so advanced that we can use proton, right? The fundamental particle to store information. So each byte is stored in 1 proton, right? And you can't do better than that, right? So if you do that, and then the proton has the mass of 10 to the minus 17, 27 kilogram, right? So if you use this probably 100 years, proton memory to store this coefficient, you'll end up with a storage that weight 1,000 kilo, which is like 1 ton. Okay, 1 ton. And you might think, okay, that's still doable, right? 1 ton is it's not crazily large, but if we increase the number to 300 atoms is not anything crazy, right? Any DNA train have more than that. So 300, then the number of coefficient you need is 2 to the 300, and that's about 10 to the 90th, okay, 10 to the 90th. And how large is that? Okay, that's actually larger than all the available protons in the universe. Okay, the entire universe has a mass of 10 to the 53 kilogram. So if you use your proton, okay, as your memory, and then you have to store this much memory, you have to use your proton memory will weigh 10 to the 63, okay, kilogram. So if you use proton as a memory source just to calculate atoms, just to calculate molecules with 300 atoms, you have to use, all the protons in our universe and probably the next universe, right, next to us, if there's one. Okay, so this is actually the very basic argument that if you want to calculate the molecules, if you want to calculate complicated systems in a complete quantum mechanical way, you can't use classical computers. Okay, you simply can't. And nowadays, how people do it, and of course, we don't have quantum computer yet. So nowadays, if you want to calculate the structure of the protein, okay, structure of large molecules, you actually use a lot of approximations, and then you find out a lot of times approximation doesn't work, and then you propose new approximations. And this is actually one of the reasons why the drug development is very slow. Okay, suppose you can do this computation, right? You know the structure of your drug, you know the structure of your, let's say, virus. Okay, then you can actually, if you have a quantum computer, you can actually simulate how they interact, and then see whether the drug will kill the virus or not, and whether this drug will kill other, molecules in your body. Well, not molecule, kill other cells in your body. And so that way you don't have to go through this clinical trial, animal trial, clinical trial, and then do over again. So, the drug development is like, usually it's 10 years period. And then the quantum computer can dramatically improve that. Okay. So let's let's lay out some fundamental elements in the quantum computer, okay, and compare it with the classical computer to give you guys an idea what's the critical difference between these two. So for classical computer, okay, the information unit is called bit, right? It's called bit, and then your storage or your computation state is either in 0 or 1, right? You have to choose 1, right? And then for quantum computer, okay, the mainstream, okay, of the quantum computer is called qubit. Okay, quantum bit, qubit. And then there's other approach called Q mode, quantum mode, which is just very similar. And then the state, okay, you can have is the eigenstate of your system. Right. So in any atoms or in any quantum system, usually you have more than 2 quantum states. But then you can choose to only use 2 of them. Right. Just like in your classical computer, you usually use voltage to represent 0 and 1. Right. You can always increase the voltage to even higher, but then we decided not to do it. Right. For example, 0 and 5 volt are very commonly used as 0 and 1. And then, yeah, so the example here is probably voltage, like low and high voltage as 0 and 1, and here could be ground state and excited state. Okay, examples. And then the primary difference, okay, a primary difference is that the classical bit has to be must be in 0 or 1. Okay, it has to be in one of them and can only be in one of them, right? And on the other hand, the quantum computing, the qubit, can be in superposition. Can be in superposition of 0 and 1. Okay, if you have other state, you can be more than that. So the information, okay, how the information is encoded. The information, for example, if your memory send the information stream to the CPU, right, then the information is a definitive number stream, right? 100, 101, and then keep going. Okay, and then for n bit, actually contain n bit information. Okay, and then for the quantum computing, the information is in the superposition coefficient, right? So you have 0, 0, if all n qubit is in 0 state, and there's one coefficient, and then there's another coefficient, all in 0, and then the last qubit is in 1, okay, and then keep going, right? And then you know there's 2 to the nth coefficient, 2 to the nth possible configuration, and then there's 2 to the nth coefficient there. So your state contain, you have n qubit, and then it contain 2 to the nth bit information. Okay, so it has n to the n bit information. Right. So you can see that there's an exponential, supremacy or advantage your quantum computer will have towards your classical computer. Now, I'll give any questions here? No? Okay. Yeah, just definition. I'll give one example on the, other than using quantum computer to solve quantum problems, what other classical problems that people know are, exponentially hard for classical computer, but have some possibility to solve it quickly by a quantum computer. One is the factoring large number into prime numbers. That one is supposed to be used to break the bank system, and then I have no idea why people are investing so much money into it, because it's like spending money to create a spy system, and then later you will see that in the later, probably in 2 weeks, you will see that there's actually quantum key distribution that physically is impossible to break, right? So what this competition is that you create something great. Well, you spend a lot of money to spy on me, and then I spend a lot of money to prevent me from being spied by you, and then there's no net gain as a society, right? Because I still keep my information, and then you don't have my information, but then we lose a lot of money. So it's a very kind of a stupid game. One problem that people probably talk a lot would be talk a lot in the next few years because of the big data machine learning thing is the optimization problem. Okay. So optimization, is apparently very useful. For example, when Amazon deliver their, ship your package, right? Where does it go, and then which truck does it load on, and who deliver it? So example of a example of optimization, 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 of an optimization problem is that suppose, okay, there's a function f, right? The function can be, for example, to calculate the time, the total time that the package arrive at each home, or can be the total time of the well, not total time, but total money or total gas spent on delivering all this package. Okay, f is just a function to calculate that, and then there's parameters x 100. Right? Suppose there's 100 different package. Well, 100 different parameters, and then each parameter can be in a state of plus or minus 1, right? Plus or minus 1. Plus 1 might means, okay, it's one thing, minus 1 is another thing. And then you would think, okay, this is not a difficult problem, right? You can kind of solve it. But then the fact is that a lot of time this f function is nonlinear. It means that the x1, x2, x3, they're multiplied together. So if you change one, you change a lot of things inside. So the optimization problem, for example, this one can be say, okay, can you find a set of x, right? Can you find a set of x that make f approach 0, right? For example, 0 could be the minimum point of the cost of delivering a lot of things, right? And why this problem is difficult, why the optimization problem is difficult, and why does it link to quantum computing? You can think of how many possibilities you have here, right? If you just want to use it, just calculate it, right? Plug in into the function. There will be 2 to the nth, right? N is the number of input or number of variables you have here. So 2 to the nth possibilities. And then even if you use the most powerful computer, you still need to calculate 2 to the nth times, right? To get all of those numbers, to get all of those f values, in this configuration, and then compare them, right? And then we have said that it's not possible when n is 100 or n is 300, right? So, but then naturally you can see, okay, this is a problem. Probably quantum computing can do something about it, because you can be in superposition of all this, and then they're just all naturally being calculated. All this 2 to the nth possibility, okay, is calculated at the same time, right? Because they're there. But then, of course, it's not that simple. If it's that simple, we've already did it, right? So there are many problems in how to actually read out the parameters, and then how to actually have a quantum speedup. And then a lot of this work are actually done now by mathematicians. And then I'll be honest, the paper published in recent 10 years, I can't even understand any of them, because like they're mathematically just too advanced, and I'm an experimentalist. I can just understand papers that are written in the early 2000s, but then after that, things are being more and more mathematical, and then it's very difficult. And then in reality, you must say, okay, well, how Google Map calculate, if I drive from here to DC, what's the optimization, right? Which route should I take? Okay, so in many of these optimization, real-world optimization problem, what people do is that they kind of reduce a problem into smaller set of subproblems. Because you think that, you take a look here, is that the difficulty level scale exponentially with n, right? If you can break it down into smaller set of n, for example, you optimize the first 10 numbers and the next 20 number, next 10 number, then the problem becomes solvable. It's kind of like driving, okay? So, from A to B, right? You have 3 routes, you choose the simplest one. If your final goal is from A to Z, right? And then you have to go through B, right? Then 3 of them, you choose this one, right? It's very simple, and then the next one is here, right? Okay, so you divide this problem into hubs, and then it's like dividing the problem into subsets of solvable problems and then combine them. And then not all problem can be done in that way. So that's why kind of people are very obsessed about using quantum computing to solve the optimization problem. Okay, and this is one example. And then so next, on Thursday, what we will do is that we define the information unit for quantum computer, qubit. But then we didn't say anything about the computation itself, right? Computation needs gate, right? NOT gates, AND gate, a lot of those gates. And next class we will briefly talk about what the gates will look like in quantum computing, and then some mathematical, basics we need to know before we go any further. Okay, that's all for today.